So we're going to start today. We are talking about kind of probing. We're going to limit it somewhat, so we're not going to be talking about SP25 scanning probes, as those are a little less common for everybody. But we are going to be talking about TP20, TP200 probes. They function very similarly. The way that you handle them in Zone 3 and ICE especially, as far as configuring, calibrating, using the probes, is very similar. And it's fairly straightforward, and also probably the most common of the additional sensors that our customer base has. If you're talking about these machines as multi-sensor machines, obviously they're all equipped with a camera as the base sensor, but the second most common sensor would be a TP20 or a TP200 probe. So I'm going to probably emphasize the TP20 side of things a little more today. But with that said, don't hesitate to ask specifics. And the only reason I'm doing that is we just have a lot more. I'd have to switch out a module or a body in order to put the TP200 on there. Not a big deal, but one other thing I want to discuss too is before we get going is I'm going to put up on my screen here. Hopefully this works. John, you seeing on my screen a website by chance? Perfect. I am just at Renishaw right here, their website, okay? So if you go to Renishaw's website, they have a lot of information that's very valuable to you regarding touch probe capabilities, specifications, that kind of thing. So the two types of touch probes that we're dealing with today, I have a TP20 tab up here, and this is all the information you need to know about the TP20 tab. We've got the PI200 interface, the module and bodies, and then the rack here, and then kind of the specifications for the different module types here. And then the TP200 page deals with the TP200. You'll see the rack is a little bit different, uses the same PI200 interface, and the module and bodies are a little bit different as well. But they work kind of on the same, I guess, wand, we like to call it, probing wand. The place where the actual body screws into the machine is the same, so you can kind of interchange in that way. The interface box, so pretty interchangeable. So I might jump back and forth and reference these pages as we get going. Also, I have up here their kind of Stylus catalog, and one of the big considerations when you're looking at a project, you're looking at a dimension on a print is, I've got a feature I need to measure. I need to measure it with a touch probe. Maybe it's a part like this, right? So we have that cylinder that's located right here. Well, that cylinder, I can measure it with my optics if I'm looking down at it, but I can only measure it as a circle. I can measure the diameter at the top of the cylinder, but that doesn't tell me about the cylinder so much, about the 3D geometry of the cylinder. Typically, what I want to know there is maybe the size, the form, or more importantly, the orientation of the axis of that cylinder. And in order to do that, I need to measure it as a 3D feature. And in order to do that, I would need to measure it with something that can gather 3D points. And by that, I mean a touch probe, right? So I could bring in my touch probe here. And if you can see that, I could come in and pop a bunch of points on there. And now I've got a cylinder. And I know a little bit more about this feature than I did before, okay? So I'll jump back and forth and kind of look at some of the different considerations there. But just as a preface of what I hope to accomplish today, I want to talk about building probes in ICE. So what do I need to do in order to actually configure a touch probe? Then configuring a cal sphere, okay? And then also configuring or calibrating touch probes, both star probes and regular kind of negative 90-degree probes. And then also, how do we use them? Some basic kind of methodology for creating CAD-based measurements in Zone 3 with touch probes. Okay, so without further ado, let's get going. Right now, I have Zone 3, again, 10.0.20, loaded up on my Flash 200 here. And the nice thing about Zone 3 is because ICE kind of uses Zone 3's kind of architecture. You can jump back and forth between ICE and Zone 3. You can't do this with MeasureMind. If you're working in a portal environment, you have MeasureMind and Zone 3 on the machine, or MeasureX and MeasureMind and Zone 3 on the machine. if you're using Measure Mine or Measure X, and you need to build a second probe or anything like that, you need to close the software in order to launch ICE. Whereas with ZONE3, I can kind of pop back and forth and hot swap. So right now, I'm just looking at the the standard ZONE3 interface here. If I want to go into ICE, I can launch ICE from this little gear that's right up here in the upper right corner. I can also get to ICE if I don't have ZONE3 launched just by going to the portal menu here, System, Ribbon, and then clicking on ICE. So ICE is the independent calibration engine, and it's just a way, kind of one of the big advantages, I guess, of ZONE3, portal, ICE, that whole environment is that in the past, the calibrations that I would make in a software were kind of native to that software. So if I had two different measurement softwares, Measure Mine, Measure X, I would be calibrating both of those softwares independently, which leads to some correlation issues. It's just not the most, functional way to do it. But on top of that, I can now program offline. So I can have an offline feed of ZONE3 on my computer, and I can write programs. Well, in order to do that, in order for that to function and make sense, I need to be able to pull the calibration data from the machine I intend to program. So that's sort of why ICE exists, is this independent software that creates a database that can then be exported to any offline seat, and then I would be in effect programming that machine, because I would have all of the calibration data for that machine, any variables, light settings, anything I'm using. I'm basically just taking that whole kernel of information and I'm bringing it into my offline seat, and from there I can write a program that should functionally transfer, seamlessly transfer to my online seat or my machine-based seat of the software, and then just run. So that's the idea there. So we're going to be working in ICE today to build these probes and to calibrate them, and then we'll be using them in ZONE3 to actually take some measurements. So I'm going to hop over to ICE real quick. When I click on this, it's going to create a little launch screen like I'm launching the software, because that's what it's actually doing. You'll see it go through its same little launched routine here. So there we are. Once we get into ICE, we have kind of the layout here is the sensors that I have on this machine are located right up here. So it's telling me that right now I have an optical sensor, but configured for this and calibrated for this machine have also been a couple of other optical lenses. So this machine is equipped with a laser, so you see the 2x high-speed laser lens there. It's not currently on the machine. The Zoom 1X lens is, okay, because that's bold. So it says right now your current sensor with this check mark is the optical sensor, and you currently have the Zoom 1X lens on there. I also have a laser down here, and so that's where you'll see some other lenses. The lenses also are, how the laser is focused, so it's going to ask me which laser I have on there. And then I have, which lens I have on there. And then I have my touch probe stuff. So you can see the TP20 body one. This machine has been calibrated with a TP20 body, but I have the option to put, TP200s on this. The machine could also have a feather probe on it. It could have a SP25 scanning probe on it. It just depends upon how your machine was built and what kind of probes that you purchased with the machine. In our case, again, we're going to be looking at some TP20/200 type probing stuff today. We'll handle the SP25 scanning stuff on just a different class, because it's quite a bit different than the TP20 and 200, and not as ubiquitous. So less people have the SP25 scanning probes. There's kind of a price premium there and all that kind of stuff. In addition to the actual sensors here, you have the lights. These are, the lights on your machine, your accucentric light in the case of a flash optics, the backlight, coaxial light, grid light, and then the ring light here. Our camera is a Hitachi color camera. Any change racks we have configured, which I don't. The artifacts that have been configured on this machine, typically you're not going to have as many artifacts configured for your machine, because your machine, if it has a probe system set up on it, was shipped with an artifact that should probably stay with that machine. But since we are a reseller here, we have tons and tons of cal spheres and laser artifacts and all sorts of stuff that just get put on these machines. They're demo machines. They move around a little bit. So that's why you see so many in our machine. Deployment mechanisms would deal with like a feather probe, or you can have a deployable mechanism for a regular TP20 probe. It would just be in lieu of having the probe be stationary and mounted on the machine. It would actually retract up into the hood here, or deploy out when I want to use it. It's kind of more designed for feather probe because that feather probe is very delicate and you need to get it out of the way so somebody doesn't just brush their hand across it and break it. And then we also have some of the actual stage calibration stuff here and rotary stuff. So we're going to be dealing today with the touch probe stuff here and the artifacts. And before we get going too far, I do just want to discuss some of the hardware kind of options here. So touch probes. We're going to talk about two different kinds of touch probes today. Let's see here. Can I get close enough? This is just a typical single probe touch probe. This is a TP20 standard force. You see the little hood on there is black, the little cover, and that just indicates to me it's a standard force. It'll also say right on the probe standard force, so you shouldn't have to guess at that. And then I have a blue one here, and the blue one is my 6-way. And the 6-way for the TP20s just means it has the negative Z. So these ones, any of them that are not the 6-way will trigger in the positive X, Y, and the negative Z direction, but they don't trigger when you pull up. Whereas if I'm using a star probe, I probably want to have the option to pull up, and that's why I have the 6-way here as well. So if you're using star probes, use a 6-way module. It's the blue one. Okay? They're for sale at the Renishaw website or here at TQI. We stock them. And so to give you some idea real quick, I'm going to hop back to that Renishaw website and we'll look at the TP20 stuff here. And you can see the different modules here. Okay? So there's my 6-way. That's the blue one. Measurement in the negative Z direction. So undercuts. That's the big difference. The rest of them, the standard low force, medium force, extended force, these deal with different styli lengths. So, you know, trigger forces are going to change based on the length of my styli because that's a longer lever arm, right? It requires a little bit more force to trigger something if it's very short versus very long. The other thing, too, is as the stage moves, if it's too low of a force and too long of a styli, just the stage movement is going to make that inertia trigger that probe. So just look at the probe length you're trying to use and then reference the actual catalog. And if you have questions, call us. We can help you with that. Okay. So there's that information right there. Some additional information if you need it. They're always willing to help there as well. And then the TP200 stuff, there's a little less options. You do have 3 different module types, the standard force, low force, and extended over travel. The other thing here too is the TP200 and 200B. The B here is important because a lot of times when people are using these TP200 probes, they have issues where they're very sensitive. It uses a different kind of triggering mechanism in there. And because they're so much more sensitive, they tend to trigger just from the movement of the machine in certain setups. And that's what that TP200B was designed to do, is to prevent those air triggers, those false triggers. So again, explore the website. And also at their website, something very helpful is just this styli catalog. This is going to go through and show you the different types of styli you can get and then break them down for you. So there is a lot of them. As you can see, different materials, length, all that good stuff. And they do a great job of explaining to you how and when you would use all these things. There's different Ruby types and kind of the calibration methodology here as well. So it's all very useful information. They also have all of the in-stock probes as well, so that's helpful too. So this should be a very kind of, the process should go like this. A, do we have probes in-house? Yes, no. If not, do you need them? Then get them. Okay, so if you need probes and you don't have them, they can be added to your systems. Not a big deal. But just give us a call if that should be the case. Once you have identified the need for probes in 3D measurement, you might start asking yourself what types of probes you want to use. Touch trigger probes like these and the TP200 probes, they're going to take single points at a time. These do not do the analog scan that you might be familiar with. That would be an SP25 scanning probe. There's going to be a cost premium there, so that's one thing to consider. But these will not do the scans. They'll just take a lot of points and then calculate geometries from those points. They're a bit more robust, a bit more affordable, but you're trading off time typically and a little bit of the functionality for spline surface or spline curves and freeform surfaces. So things to take into account. Once you figured out and identified the type of probing system that you need, maybe look at the geometries on the print that you're trying to measure and ask yourself, do we even make probes? Typically, the smallest probing size, ruby size, we're going to get down to is about 0.3 millimeters. Okay, 0.3 millimeters means there's a limitation to how small of a hole you can get into. Okay, and the reason for that is just mechanical, physical limits. If you make something that's even smaller than that, we have to have a shank, or the part below the ruby that the ruby is attached to has to be smaller than the diameter of the ruby. Well, when we get down to a 0.3 millimeter, the shank on that's like 0.2 millimeters, and there's just not a lot of material there. If you look at those things funny, they break. So those are the kinds of things to start asking yourself. And then maybe the types of materials you're trying to measure is also an important consideration, because there is a force induced on the material when I take a hit, when I push the ruby into that material. If it's silicone or something like that, something soft and flexible, it's going to deflect, and it's going to give me an incorrect value. Okay, so if we have really soft materials, there's solutions for that. That would be your feather probe. Okay, but it's a different type of animal, a different type of triggering mechanism altogether. Okay, so once we've done that, once we've identified all these things, we have our probes, our probing system, and when you buy a probing system, you're going to get a calibration artifact with that. I've got a couple of different cal artifacts here. This one right here, kind of a very common 45 and 45 calibration artifact. 45 because the artifact is rotated this way 45, okay, as you can see there, but it's also got an elevation angle of 45. So if that's 0, that's your 45. So good for the single probes, okay. Well, not so much fun with the star probes, because it's going to get this one nicely and this one nicely, but then when I get over here, I've got this stem to deal with that's going to kind of maybe argue with my number 1 probe there. So something to take into consideration. If you're going to be doing a lot of star probing, I recommend something like that, where you have your probes kind of oriented positive 90 elevation angle, and that way I'm never having to deal with this stem getting in the way of anything. So, okay. These things can be kinematically mounted, so there is a little crow's foot pattern on there. So I could have a permanently mounted base on the stage, and then this thing could pop off via magnets and then put it back on. It's in the right location. I can use it again. But today we're going to look at configuring first our artifact. Okay, so we need to configure an artifact. We do that in ICE. I'm just going to pop back over to ICE here. And down here is where my artifacts are. I'm going to just right-click on artifacts and say configure. It's going to ask me what kind of an artifact I'm trying to configure, and these are my options here. So there's a rotary artifact, a laser reticle, a ring gauge, which would be used for disc probes, and then a sphere, also an alignment reticle. The alignment reticle is the glass reticle that comes with the machine for aligning the optics. Okay, we're going to make a cal sphere today. And a couple things it asks me. Okay, well, first give it a name. We'll call it training test sphere. Okay. Use last known. I can give it, or I want to add the serial number as well. The QBI, spheres will come with like a little sticker. You can see it right here. It's not usually on this when it ships. I would put it on there, but it does have a serial number that you can then put it in the machine, and that way I can just look at this and go, oh, this is the right sphere. Okay, otherwise laser etch it in there. Just mark the thing somehow so you don't have to guess and go and measure the sphere to make sure it's the right one. So I'm going to put that number in there. Mine happens to be 6573, so there it is. Okay, use the last known location here. This deals with if you're going to permanently mount that sphere onto the stage, and that way the machine knows where to go and find it to do a calibration. But not all of us have the stage real estate to just leave a sphere on there, so I'd leave that to false, or I will in my case. and you can tell it what type of material it is. So they're either going to be black anodized, white ceramic steel, reflective steel, or ruby. This is just helping the machine. There's some little canned routines in there to measure this sphere and then to run the calibration cycle. Well, when it measures the sphere initially, it's going to do it with the optics. And it's important that it knows what the material type is so it has a good chance of setting the lights correctly. That's kind of the big consideration there. In our case, we're using a black anodized sphere, so I'll leave that. The sphere location is unknown because I haven't even put the sphere on the stage, so I'm going to leave that. And the azimuth angle. The azimuth angle is rotation of that stem about the x-axis. So in my case, if my x-axis is pointing in this direction on my stage, this would be, it's counterclockwise, that would be 90. That would be 180, and then 180 and 45 is 225, right? So that's, check that for me. Okay. All right, so I'm going to put in 225. This is not really that important. This is just so the machine has a good guess at where that stem is. But before it said 0 and 90, and the reason was this doesn't actually have rotation about the z-axis. It's perfectly oriented with the z-axis. So the azimuth angle in this case would be 0, and then we have to do with the elevation angle, and these are the two different options here. This is 0. This is 90. This is negative 90. Okay. So in our case with this white one, it's a positive 90, and then in the case of our sphere here, it's 45. So I'm just going to type in 45 for an elevation angle on this one. And the IJK will be populated, and that's the vector orientation, and that's populated using those two values there. Then we need to put in our certified diameter. What is the certified diameter? Well, that should come from the cert that's shipped with this CalSphere. Okay, you'll get this CalSphere in a big wooden box, and inside of that big wooden box is going to be an envelope. The envelope will have a certification of calibration from whomever made the sphere. In this case, QVI is typically who these ship from. And the reason you can't just measure it on one of your machines and call that the known size is because we have to be much better. We have to be much less uncertain or more accurate than the machine we're calibrating, or the gauge or tool we're calibrating in this case. So, you know, we can calibrate these spheres, I believe, here, but typically you need something that's super high accuracy. You need a very high accuracy lab and a very high accuracy CMM to calibrate these things. Hey, that's us. More QBI, but this will ship with a calibration cert, and there will be a size of that sphere on that cert. And so go ahead and type that in. I do believe this one is 20 millimeters, but I'll just use, I think this is already a built sphere for me, so I'll just type that in. And then the shaft diameter is a little less important, but they're typically 10. Just measure that one with a caliper. It just needs to know roughly how big and where it is so that it can try and avoid it, okay? Once you're done, you hit finish, and happy days. Oh, I can't have spaces in the name, so I'll replace those with underscores. Okay, they do limit some of your characters in these softwares because they use them for variables. So I'll go ahead and hit finish, and then I have it right there. Now I can use that, okay? And the whole principle here is, if I know exactly how big the sphere is, and I know roughly how big the ruby on my stylus is, I can go and measure the location of that CalSphere with the optics, calculate the dead center of it, and then I know the size. Now, if I go and measure that sphere with an unknown ruby size, I can then also back calculate the exact size of the ruby, the sphericity, and the location of the ball center. So I need to know the offset from basically my optical focal point, which is the business end of the optics, to the dead center of the ruby in each case. And we'll just basically bake that in a calculation between the sensors, okay? So we've created our sphere. I'm going to go ahead and delete this one because that'll just be hanging out in there. And I know I already have this thing built. I think I call it Sphere Northwest. And how do I know this is the right sphere? Again, look, I got a sticker on my CalSphere that tells me its serial number is 6573, and there it is. So my actual diameter on this is 20 millimeters and 1/10 of a micron. So the calibrations are really good. They're submicron, which is just so much better than this machine is capable of. Yeah. Okay. The next thing we need to do is build probes. Do we have any questions on that? Nothing yet? Okay, good. Okay. Yeah, go ahead, and if you have any questions that are just kind of, you know, live questions where something's not making sense, feel free to throw them in that chat. I tend to ramble. So now we need to build touch probes, okay? So the first thing we're going to do, when this machine gets installed, we are going to, when this machine gets installed, it's going to get installed with everything set up, okay? So out of the factory, if you order this with a TP20 probe, there's going to be a TP20 probe already configured in ICE. If there's not, we're going to do that when we install the machine and calibrate your probes. If we've installed a TP20 or TP200 probe after the fact, you know, as an upgrade, we're going to do that same thing unless you tell us to not do it, tell us otherwise. So let's walk through doing it anyway, though, so you're kind of aware. In our little sensor tree here, this is where we need to talk about building probes. So if I go to the sensor level, that would be the furthest up node on any one of these sensors. So that'd be optical sensor, QBI laser, touch probe. I'm going to right click and say configure, and now I can add a tool. Now adding a tool would be adding something along the lines of an actual body here. So if I say, okay, I want to create a body, it's going to say, is it a TP6, TP200, TP2, or TP20, or a feather probe? These are just different types of probes we were talking about. But again, the two we're talking about today are TP200, TP20. Now, if I look over here, I've already got a body, a TP20 body set up. I don't need to do that again. It needs to be done once. And this is where I was getting at the fact that this will be set up when the machine is installed. So rather than build a new body, I need to build styli. These guys, right? Mine's got a paper clip on it. So in order to do that, I'm going to right click at the same location and say configure and add a stylus. Okay. So to add a stylus, I am working with this machine right now, the TP20. So you can see right there is a TP20 body on there. And the first thing it's going to do is give me this little list. And it's going to ask me, what probe module are you using? So I have two of them here. I have a TP20 5-way, or 6-way, I'm sorry, the blue one. And I have a standard force black one with a 2x20 stylus on it, okay? So the first thing I need to do is select the correct module. So I'll build the standard force one first. TP20 SF down here on my list. That's what the SF refers to as the standard force. But it also tells me who the supplier is and what the part number is. So if you're not 100% sure, when you order these probes, they have a part number with them, with the modules and all of the styli. So I double click and look at that. It adds that module right to my little graphic here. Okay, helpful. Because as you're building these, it's going to kind of look right or look wrong. The next thing it's going to do is ask me what happens after the module. So when I say what happens after the module, I say that because it could be as simple as a single stylus, like in this case. I'll put it in front of my face. Let's put it up here. No, okay. It could be as simple as a single TP20 stylus like, or I'm sorry, a 2x20 stylus like this, or it could be something a little more complex like this, where I have an extension and then I have a star at the end. Okay, these things can get pretty complicated as far as how you want to build them. There's lots of different varieties of probes for lots of different scenarios. A shank probe, if you need to get into an off-axis bore, something like this right here. You see this hole. Well, you know, I'm not going to have a whole lot of luck getting down into that hole. This is interesting. There you go. I'm not going to have a whole lot of luck getting down into that hole with this, because this is going to be oriented incorrectly. But if I had a probe that came in like this, that'd be great. So you'll see on CMMs, a lot of times they have indexing probes like this, where I can actually index the probe around. The reason we don't really see that on OGP machines, although it could be added for a fairly premium price, is that we don't have as much stage travel as the CMM does. CMMs, you know, oftentimes they're 3 feet deep and 3 feet wide and 4 feet in Z. Well, now I have all the room in the world to index this probe around. Well, on this TP200, you know, we're 12 by 12 by 8. So we don't have all that room to be indexing these probes around. So we have to kind of come up with different solutions for getting into those stranger types of features. And then there's also the consideration too, you know, there's times when a part is more of a CMM part for those types of reasons. If it's stuff that needs to be probed on all over these different work planes and different axes, that's, you know, an indication usually that maybe it's better suited for a CMM. But that said, we have plenty of probing capability in here. So let's go ahead and build our first probe. We've already chosen the module, and now we need to choose a stylus. In this case, I'm not using a connector, which would be if I'm building a star, custom star, or having one of those shank probes that turns like this. I'm not using an extension. This is just a straight up 2x20 stylus. And it's not a fixed star like that one is there. So in order to do that, I'm going to look at the stylus list here. Now, this is a list of all of Renishaw's styli in here. You can still get custom styli that are not in the catalog here from Renishaw or from other stylus builders. And QVI has built into the software a little custom probe builder. So you can actually make these kinematic models for custom one-off probes. It's just a different thing. But in this case, this is a tip diameter of 2. I type in 2. And now it's limited this whole list to any of my probes with a 2 millimeter ruby. And now I've got a 2x20. Okay. And it's an M2 thread, diameter 2 ruby, length 20, effective working length is 14. And then the diameter of the shank is 1.4 millimeters, and it's stainless steel. That's kind of how you read that. I also have the part number here I can work with from the catalog. So if I double click on that, there's my new probe. Okay. The one thing I have to do is I have to call it something. And I'm just going to call it training 2 underscore or 2x20. Can I do that? There we go. So there's going to be some characters you can't use. And that's something that I would really recommend you guys consider when you start to build probes, especially if you're going to try and share programs between MeasureMind and ZONE3. You know, if you're using Portal, you can't use spaces in your probe names, but you can in legacy versions of MeasureMind. So that's a big difference. That is now a completed stylus. And now we would just need to calibrate this thing. Okay. The next thing I'm going to do, though, is build out one more stylus while I'm in here. I'm just going to hit save. And now I can say I want to, excuse me, right click on this here. It's giving me a little delay. And click create a stylus. I'm gonna build another one. In this case, I don't know everything I need to know about this particular stylus. So I'm gonna help myself out, and I'm gonna grab a caliper or some other common measurement device. We've got a few of them hanging around here. There's a little 8-inch caliper, 6-inch, 8-inch, 6-inch caliper. And the reason I'm doing that is because I just grabbed some random stuff out of our drawer or probe drawer or stylus drawer, and I want to make sure I get all the right values in here. So ruby sizes, lengths, all that kind of stuff, the length of this extension, length across these, that kind of thing. Now, it is baked into the software, this actual probe. I just need to make sure I pick the right one. And if you're not certain about the probe that you have in your hand, it's a quick way to determine ruby sizes and length and that kind of thing. So get your caliper out, get your caliper skills going. And let's go ahead and build this one. So first off, I need to say, what kind of a probe is it? Well, I'm using the blue one, the 6-way module right here, 6-way module, because I'm going to be doing some pull hits where I'm going to pull up, up, in the negative Z direction, okay? So my 6-way is the 6W, TP20 6W. There it is, nice and blue. Now, I do have an extension on this one, so I'm going to go ahead and figure out how long that extension is, okay? The extension, I know how long it is, but I'm going to measure it. And I measure it from the shoulder of this module down to where it ends. And I'll give that a look. And it looks like it's 29.99, so I'm going to assume that's a 30 millimeter extension. So if I click on my extensions here, the most common ones are up top here. It's an M2 thread, the extension, it's a length 30, diameter 3 millimeters, and mine actually is stainless steel, so it's not ceramic. If I pick this one, it's going to be kind of white. It's hard to see, but that's because it's a ceramic extension. I'm not using that. I'm going to delete that over here, and I'm going to look for the 30 millimeter extensions. Can again type that filter in, and it's the same here, except mine says SS, stainless steel. So I'm going to choose the stainless steel one. Not the biggest deal in the world, but that's if you want to make them all look right and everything. After that, I have not a single stylus, but a fixed star stylus. So I need to know a little bit about this fixed star stylus. And this, you can use the part numbering. When you order one of these, you'll have a part number. But a couple of the things it's asking here are, first of all, how many balls is it? Well, mine's 5 balls because I've got the 1, 2, 3, 4, 5 probes. Okay, and it's also going to ask me what is the diameter of these rubies. So I can go ahead and just measure one, and it tells me I'm at 2 millimeters. So I can rule out a few of these right away. Okay, so it's either this one here or this one here, because these are the two with the diameter 2s. Okay. Then I need to know the length of each of these styli, and then the spread is the spread across these things. Okay. So the length of the styli here is going to be 19.25, and then the spread is either 20 or 30. Now the spread in this case is across from one of these to the other side, from the center of the ruby to the center of the ruby. Okay, so mine appears to be 30. So it can only be one. It's the diameter 2 5-ball with the spread of 30, S30 spread. Again, I would just use, if I wasn't certain, I could just use my actual part number to determine that as well. The other thing about star styli that I might as well touch base on is there's little holes, kind of keyway holes, in the cylinders of these different styli. Okay, they are the same size as a paperclip, but they also come with like a little tool that you can use, but the tools get lost and then you can use a paperclip. So there's one right at the base of this extension to tighten that down, so I can put the paperclip through and turn it to tighten it. But in these particular stars, it's this probe that locks down this fixed star on here. So this star can spin, it gets locked down by this bottom probe here. That threads up into the extension and kind of hugs this star here and locks it down. So that means that it can go onto your actual body disoriented or oriented incorrectly. So in order to get that thing oriented along the X and Y axis of the machine, you're going to want to mount this up onto the actual body on the machine, so it's on there how it's going to be. And then we're going to get this thing kind of oriented the way we want, the star. And then we're going to get this thing finger tight and then get it just about a quarter turn away from square to the X and Y axis, and then tighten it down. You can always go back, but you got to be close enough. The things to consider are the fact that if I'm coming in here on a feature like, let's say, for example, this one, this little cylinder feature right here, I want to make sure that my stylus is oriented kind of parallel with the axis of that feature so that it doesn't come in all cockamamie and take bad points for me. So it's just, can I get into my feature and will my probe shank out? And when I say shank out, I just mean if your probe isn't coming in square to the feature, you might actually be touching on the stem and not the ruby because it's not square with the axis of the feature. So all that kind of comes into play, just trial and error, or, better yet, give old PQI a call when you're having trouble with it, and we can help you and walk you through it. Training is also a good thing to consider as well, because it's nice to see it from the horse's mouth in real time. So now I'm going to give this one a name. We're going to call this Training Star. Okay, I'm going to save that, and now I have a couple of probes over here. I've got my Training Star and Training 2x20. Now, just a little note, if I double click on one of these, it's going to ask me to load one of these probes. These are the probes that I've already built and configured, okay? So if I double click on this one I made earlier, it's the 2x20. Notice it's green. Now, this isn't the same 2x20 I just made. This is one I made earlier and calibrated it. It's green right here because this is a calibrated probe I can use. It knows everything about this probe, so therefore, green, I can use it. If I right-click and say detach manually and go and load my Training 2x20, the one I just made, it says put that on the machine. It's red now. It's red because it hasn't been calibrated. I would not be allowed to use this in a program. It knows that I've configured this probe. It knows that it's there and kind of the rough size and everything of it, but it hasn't been calibrated, so it's not usable for me. Otherwise, I'd be getting all sorts of bad data. So we would need to calibrate this thing. So I'm just going to say detach manually, right-click at the actual stylus level, say detach manually. And now we're going to go and walk through how do we calibrate these things. Okay. So in order to calibrate them, I need to take what probe I'm going to use. And I'll calibrate for time's sake this probe, and then I'll calibrate 2 or 3 of the styli here and just leave the other ones because it's just more of the same. But I'm going to put this one on the stage using 2-sided tape. Okay. I'm going to make sure I can get at the number 2 probe, which would be the one pointing towards the back of your stage. I'm sorry, just to the right of the stage, and then the number 3, which is pointing back to the back of the stage. So your number 1 is always pointing down. Number 2 would be pointing to the right if you're looking at the machine, and then it's counterclockwise. Number 3 is back, number 4 is that way, and number 5 would be pointing at you. Okay? So I got 2-sided tape. Mount yours down with something. There's threaded holes on the stage. Make sure you can get at the actual cal sphere. The other thing to consider is these probes are off-axis probes, so you got to make sure that you can actually physically get to them. So drive your machine around and make sure that you can physically get to the cal sphere from all the different orientations you're going to need to. Okay, so I've got my cal sphere artifact already configured. It's in the machine here. And in my case, I called it Sphere Northwest for some reason at some point. And I've got my styli already built. So I've got the 2 new ones, the Training Star and the Training 2x20. These are what we're going to calibrate right now, and then we can use them. So the first thing I want to do is to go to Qualification, Sensor Offset. Okay? That is going to be calculating the offset between my sensors, which is what we need to know. The offset between the ball center of each ruby I intend to use and the optical focal point. Okay? So my configured artifacts are right here. These are the artifacts that it presents to me as an option to use based on the sensor I have currently selected. So I'm currently have the active sensor set as my optical sensor, which means I can use any of these. If I change that to touch probe, notice a lot of them go away because I can't use that. I can't use the touch probe to measure some of these, okay? If I go back here like a laser, some of them will go away, right? Okay, so we're going to use our optics to first measure the location of this cal sphere, and then we're going to use our probe to measure it to back calculate the location and size of these rubies. So it's Sphere Northwest. I've got it selected. It tells me the serial number. Good to go, and I can hit next. Real quick back, if you do have it permanently mounted and use last location is set to true, then you could just hit go to XY and it would drive the optics right to that cal sphere. But since I just obviously put this on stage, yeah, I'm not going to do that. Then I get a couple of options here. Use the current location as a safe height. If you do have some tall fixed string or stuff like that on there, you can use that as a safe height. It's not going to just take off and run into anything. Unless you have that use last location set to true, so something to consider. Number of cycles is you could have it run through several times and give you an average to try and improve your accuracy. And then there's some options in here to set up the light settings automatically or set them up manually. Really doesn't matter. We're going to use the optics to measure this cal sphere, so it's important that we have some lighting that we can use there. And then the measurement parameters here is number of retries. If it fails to measure an edge, how many times it's going to retry. Number of focus averages, it's going to measure the OD of that cal sphere, the equator, and then measure some points at the top of it in order to calculate the sphere's location. So you can set that to whatever you want in order to try and again, increase some accuracy. But I'm just going to stick with the defaults. They're fine by me. And now it says focus on the right edge of the artifact, then click the next button to begin the measurement process. So it shows me here with an image what I'm supposed to do, okay? I want to go and make this image over here, my camera, look like this image over here. So in order to do that, I'm just going to manually drive to kind of where I think it is. I can move it down, move it up a little bit. But once you get kind of where you think that image is now starting to appear to be similar to this image, I can hit next. And I can hit compensate, and now it's just going to start doing its thing. So it sets the lights automatically. It's going to go through a focus here, and then it's going to go around and measure the OD and then measure some focus points at top dead center of the sphere. Oh. Any? We good? Okay. Hopefully nobody didn't get picked up. But weird noise. So once it's done, it's going to tell me everything worked out, or it's going to give me an error. Is the audio from the TV? Okay. So it says the qualification is complete. It's completed. If I hit next, it's going to automatically create a record, and this goes into a log. Okay, it just says, on this day at this time, I measured that artifact. This is nice, because there's always going to be a record that you did something calibration-wise you can always go back to. And that way, when Randy on third shift says he actually went around and calibrated the probes, you can go and check. Just kidding, Randy on third shift. We believe you. Okay. So you can just close this, and it says now at the top here, use the sensor tree on the left, this thing here, to activate a sensor being optical, laser, or touch probe, and tool. Okay, so in this case, I'm going to activate by double-clicking or right-clicking and say activate the touch probe. And then I need to add a tool. So I'm going to use training 2x20. It says, I double click on it. It says, attach the following, 2x20. I'm going to go ahead and put that on. If you've never used these probes before, right on the body here, there is a series of symbols. There's a triangle, a half circle, and a half. I guess it's a half a diamond, half a circle, and a half of a rectangle. And then the other half would be on the module, and you can just kind of marry those up. It does just kind of clock on there one way. So if it's not sitting nice and firm, then you probably don't have it on there correctly, but make sure you got it on there nice. You can kind of give it a little twist, and it shouldn't twist on you. Okay, so now it's on there. I can hit OK. And I'm going to hit next. So it says you've got the touch probe as the active sensor, and the current tool on there is the 2x20, and it's red. So it's not calibrated. You can't use it. I hit next. And it says some more of these kind of default settings. Are we just verifying whether this is correct, or are we compensating, which will actually update the values in the cal database? The number of cycles, again, would be an average. Number of the artifact coverage is if I've got a very small probe and maybe I can't quite get to that equator without shanking out, then you could reduce that number. It's only going to go up to 90 though, because obviously I can't use a probe to come and get on the underside of this. And then the number of points, you can either do 5, 9, or 25. I'll just do 9 to kind of give you some idea. It says position the stylus tip normal to the artifact, and that just means top dead center. I'm going to do that. And once I get my probe sitting right over the top of this, and I just got to be kind of close, maybe a couple millimeters above it. It's going to take 4 points to make it, to just kind of locate that sphere, and then it's going to come back and clean it up. So I'll just hit next here. And what do we got? It's going to take 3 points. Oh, hold on. There we go. Okay. Little feedback from our actual machine here. This is a work in progress. So now it's going to go around. It takes 3 or 4 hits to kind of roughly locate the sphere. And then I told it to take 9, I believe, unless I didn't change it the second time around. 5, 9, or 25 hits to actually calibrate the ruby. Once it's done, it's going to say, hey, it worked, or it didn't work. It says completed. Qualification is complete. Down here, a couple things we can look at. It says that the cal sphere radius is 9.995799, and we know this to be just about 20. Exactly. So we're, within a couple of microns there. And then our tip diameter is 1.991498. It should be 2. Yeah, well, and our sphericity is about a micron right there. So these are good numbers. We'll hit finish. We store our offset. Yes. And then it creates another one of these records that we did this, okay? So I'm just going to quickly go through part of the star probe, and then I want to save some time to actually do some probing, so I'm not going to do the whole thing. So it says, you're about to close this wizard. You will be required to remeasure your artifact upon re-entering the wizard. You sure want to close? No, I don't, actually. I want to do again. I don't want to hit finish, because I want to detach this probe and load a different probe. So it says, okay, let's use the sensor tree on the left to activate a sensor and tool to be qualified. I'm going to do the training star, double click, it says okay. And now, oops, did I pick the wrong one? Training star. Okay, so this one you'll see has 5 tips because I made a 5-tip star here. So I have to both choose the actual probe and then the tip I want to use. Tip 1 is this tip, okay? Tip 2 is this tip. 3 is around back, 4 is on this side, and then 5 is up in front. So that'll always be the case. It's down 1, 2, 3, 4, 5. Okay. So T1 is going to be my downward facing probe. I'm going to hit next. I'm going to use the same 5 points, all this stuff. Hit next. I know I need to get it close, so I'm going to just bring it down a little closer, and then I'll hit next. And then the thing's going to go in and do its automated little calibration routine. And I'll do this on tips 2 and 3 as well. So this is kind of one of those things where we definitely hope for questions and feedback from you, because even in a training setting, we can kind of walk you through, here's how you build a probe, and here's how you build a star probe, and those types of things. But everybody's challenges are so unique that we can't possibly go through every scenario you might come up with. So it's important that you understand the fundamentals of how to do this stuff, and then when you get to those challenging one-off scenarios, you give us a holler. So we've completed that. I'm going to say again, I'm going to store the offset value. I can minimize that. Now I'm going to do tip number 2. Double click on it. That becomes bold. That's now the current tip. And I say next. And now it's going to change my little graphic a little bit. And it says, make sure you're normal to the sphere. Now, normal with the tip number 2 is not going to be right above it. It's going to be pointing at it from the side. So think about an arrow pointing straight out of the probe tip. That's your normal. Okay, so I'm going to go ahead and get close again. And once I'm close enough, it can kind of do its thing. I hit next and let it rip. Now you'll see it'll be coming in from the side. And it just basically does the same thing. Okay, and I'll do one more. Again, I want to get to the actual probing stuff here. So I'm going to say yes, store the value, minimize this, double click on T3. Now this is going to be the tip that's pointing straight towards the back. So I'll get it close, hit next, and then next. You can feel free to play with those parameters as you see fit. And really that's kind of one thing I wouldn't recommend against, I guess, is, you know, click around on stuff and see what it does, ask questions. It's the only way you're going to really kind of dig deep in this software. You can use it at the surface level, or you can go very deep on it, and it's sort of up to you. But I guess with any of the softwares that we work with here at PQI, it's in the hands of the user, whether they're going to become a really high level, expert level user or not. We got a question. What touch speed do you use? Can you use a standard module with a star, or does it have to be a 6-way? Yeah, you can use a star with a standard module, but you can't do the pull hits with any accuracy. So if you want to pull upward, you're not going to have a whole lot of luck. And then what speed do you use? There's default speeds built into the software that QVI recommends based on these controllers. Those can be adjusted. I'll show you when we create a step. You can adjust them a little bit, but in order to get the accuracy out of them, you don't want to start playing with those too much. That said, if you have specific applications in mind, please let me know, and we can kind of take a look at that. And I can even get QVI involved if it's something that you really want to know if I can go to this speed on this with this setup. But it becomes kind of unique at that point. So I'm going to say finish here. And I've got now these qualifications here. I say yes. I'm just going to close out at this point. I'm going to unload this training star, detach manually, okay. And I'm going to make my optical sensor the current sensor, and then I just close this, and it should drop me right back into zone 3. The nice part being that I should have some additional probe options in here. So you see down here in my sensor tree, I have training 2x20 and training star. So let's go ahead and now mount our part on the stage. I'm just going to throw one more two-sided tape on there. Again, feel free to be better at this than I am with regards to holding your parts down. We're just doing stuff on the fly here. And there it is. I'm purposely putting it somewhere that I can get to the additional features I want to get to, by looking at where my probe is relative to my part. So if my probe is going to be here, I know that I can get to the stuff I want to get to on this side, but on this side I should be good too. But if I move this part all the way to the left-hand side of the stage, I wouldn't be able to get to certain stuff on the left-hand side of the part, if that makes sense. Okay, so let's go ahead and create a quick optical alignment to the part, something I always like to do. The optics are a bit more forgiving than your probes are going to be. So if you're not aligned to your part and you start making automated probe paths, you're going to have some issues. So what do? Well, we import our CAD. It's kind of a little review of what we did last week. I'm going to go ahead and use a part setup after this imports. So there's our CAD model. I want to say a manual part setup. I'm going to use that location there again, just because this makes it easy for me to just start programming right off the rip. And I'm going to go ahead and hit save. Now I need to go and create that alignment, right? So I'm going to go in and get my crosshair tool or a manual tool. I can always do a focus first just to make sure my Z height is set correctly. So I grab this focus tool up here and say focus. I close it now. I don't have to deal with a point being created or anything like that. And now I can just come over, I hit run. This is free now. I'll do it this way because anybody with slightly older software will have to hit run before these things are live. It's like hitting run in Measure Mind or Measure X. That's going to be my XYZ0, that location right there. I'll move this guy out of the way. And you can see right now that my field of view graphic, which is this cube, agrees with what I'm seeing over here. That's what I want to see. I'm going to move down here. And what the software doesn't know is that my part is kind of skewed a little bit. So here it thinks I'm perfectly on that corner, but I'm not. Now I'm perfectly on the corner, but it doesn't understand that I've got a little bit of rotation. So if once I hit the skew button, that sets that rotation, and now it's just ever so slightly skewed like it is on the stage, which is what I want. So from here, I could just start to program, and I'm going to do that. I'm just going to go and measure a plane and a line and a line. So first thing I want to do is I want to measure a plane. I want it to be a continuous feature. I want to use this plane right here. I'm going to go into high mag because I'm going to do things right so as not to confuse everybody. You always want to be at high mag when you're doing focus points because look at my depth of focus. So small, so small. Okay. I'm going to set my lighting where I want it. That looks to be good. Right here is the surface. And I'm going to use a focus target, and I'm just going to take 4 points. Now, because I'm aligned to the part, because I did that part setup, I can just place these points. If you haven't aligned your part in any way, manually or via the part setup, don't do this because it's just going to drive where it thinks your part is, but you're not aligned to it, so you would have some issues there. Okay. I'm going to call that A. I don't know if we'll need to use any datums, but we'll call that A, hit save, and I'm going to go to low mag. And I'm going to measure this front edge. And we'll use a named lighting set. Let's just 50 back low. And our front edge is a line. So again, I want that vector pointing out of the front plane. You see that pink arrow? That's what I'm talking about. That should be pointing out of the front plane, not off the top plane like that. Okay, so if my cursor is actually on top of the part, that vector arrow points up. If it's associated with this front surface, then it points out. And that's what I want. I really want something on my control there. So now I've got these 2 lines is what I'm associating to. It says this curve and this curve are one feature. They're one line essentially. And I'm going to call that datum B. And I'm going to change my tool here to the feature finder. And now I'm just going to say generate a path for me. I can see what it's going to do here. Otherwise, the other option I have is I don't have to use a path generation. Did I not go to low mag here? Looks like I did. So make sure you're at low magnification. I should have looked at that field of view and saw that it obviously wasn't. So I'll use my path generation here, say generate a path, and now I can kind of see using this display test path which direction it's going to go. Now I want it to go this way because I wound up here with my last focus point. So I'll say reverse the path and then generate it and hit OK. And now I can just hit run. And look at that. Saving time. Okay, we're going to save that, and then I'm going to do one more line on this left edge, and I'll call that my datum C. I'm going to say what I want to measure, where is it on the part I want to measure that feature, and click those three edges. Again, associating to the bottom plane here so that that arrow is pointing out, and then I'm going to use my feature finder, generate a path. And why am I generating the path? Why don't I just go and manually take these? It's just quicker, it's cleaner, and then I'll reverse that path. You can always play around with the path generation until you get exactly what you want. Makes things a lot easier. I'm going to go ahead and run that. And I hit save. First, I'm going to call that datum C and hit save. And then I've got my alignment features. So now, go ahead and get my 3D view back here. I'll create an alignment and I'll select my plane. It locks it to the plane, which is controlling 3 degrees of freedom and then the additional 2 degrees of freedom off this front edge. And then a fully constrained alignment so the trihedron is no longer floating around. So now I'm ready to start using my probe. I'm feeling pretty confident about it. So I'm going to come over here and say I want to change my current sensor. So if I click on the bottom ribbon here, I can click down where it says touch probe, and it says which one do you want to use? And I want to use my training 2x20. Okay. So I'm just going to manually load that onto the machine. Okay, I hit OK. And if I turn my probe on, you should see that probe model graphic hanging out where it is relative to the actual part. If that doesn't look right relative to your part, then something's not right. So now I can go and start to probe more 3D type features. So I'm going to probe a cylinder here. And I always say what I want to do, what type of geometry I want to measure, where is it on the part, right there. And what do I want to use? Well, I want to use my touch probe now. So it says, okay, you can just start taking hits or clicking here to take points like that, right? But that's not very accurate. You'll see how they're just willy-nilly placed there. This is where path generation becomes very helpful. Okay, so now I'm using a circular method where I'm going to go around in circles and then drop down, and I'm going to take points that way. The other option I have here, or one of the options I have now, is I can see where those points are going to be. These little ruby graphics here, those are kinematically correct. So those are actually the size of that ruby, and this is actually the CAD model. So I can see, well, I got a little offset from the bottom plane here. That's good. A little offset from the top plane. If I want to make that smaller, I can say, you know what? I don't need to be that far down from the top surface. So let's make that 1.0, and then they hop up a little bit. Okay? Let's say I had no offset on the bottom side. Okay? Then it would just get rid of that bottom row because it would recognize that I can't do that. So I'm going to go ahead and add that, and now they're, oops, see that 1.05, they're probably going to actually touch the bottom surface there. And you can do a little math. I know this is a 2mm ruby with a radius of 1, so I probably want to be at least 1 millimeter off the bottom. Okay, number of points and number of sections, play with those however you want. But once you've got what appears to be a reasonable amount of points, you know, different strategies here, by the way. Longitudinal is just going to go in a column and then go around and then another column and then another column. Or helical. Helical scan paths will actually allow you to kind of ride on the thread for a threaded hole. If you wanted to locate and do a position on a threaded hole, you can't just take points wherever because you might be on the minor, major, at different points. So if you actually ride the helical pitch, then you'll kind of have consistent points on the actual thread, and then you can calculate an axis and location and that stuff. We're going to go ahead and stick with our circular path for this. And I can use a starting safe and ending safe height here. So I can turn those on or I can turn them off. If I do this and I try to run this program right now, this probe is going to want to drive directly to the first hit. Now let me just make sure that my... Okay, I'm going to put one hand on the start stop button. I do believe I have my collision detection turned on, but if I don't, then I want to be able to stop this. If I hit run, my collision detection is turned on, it should say, hey, that's not going to work. So that's what it says right here. It says a potential collision was detected within step cylinder 1 and finder probe 2 moving to point 1. So either continue, it'll let you just drive into your part if you want, or you can hit cancel. In order to kind of show you what it was going to do is I can just test the path. See, it's just driving right to the first point. It doesn't know any better. And it also allows me the override option if I know that there's material missing on this part versus the model. But what I need to do is I need to create some sort of a safe approach, right? So I want it to kind of start above that feature and then go down and then probably retract to that feature. So right here I have add approach from clearance zone and add retract to clearance zone. And what that's going to do is at the beginning of my little probing strategy, it adds this clearance point. Now I can make this clearance cube bigger or smaller, depending upon what I want to do. But what you need to know is it's not going to violate this cube on its way to this cylinder. So it has to drive up and then over and then down it. It prevents me from actually hitting anything. So now I feel pretty good about running this, but I would always say, you know, maybe turn your speed down, keep one hand on the start-stop button, that kind of thing. Go ahead and hit run. Again, I'm going to make sure that my program marker or where it's going to start from is up here. That's one thing to consider too, because I'd probably get that same error if I just tried to run it from here. Once I hit run, the machine drives up to the clearance zone, and now it's going to drive over there and start to measure the cylinder. I can move the kinematic here, the model if I want to see what it's doing. All that can be adjusted in real time. You can make the model transparent so you can see how those hits are being taken. So you can see they're taking hits nicely. I mean, again, compared to Measuremind, it's a little bit easier. And this is exactly how it would behave in an offline seat. And this is what allows you to do offline programming, is because it knows everything about the nominals and the relationships between the features. You can actually program just like this, although you're not going to, you know, obviously we're not going to have a part there in a machine. But the idea would be that you've downloaded the calibration data for your machine, and now you would have the probes available and all that stuff, and it would work once you put it on. I'll just kind of show you an example too of, you know, maybe something that's a little bit more complicated. So like another feature type would be, let's say, a plane. Okay. Well, there's going to be times when it doesn't really pay to use the auto pathing, just because, like in this case, this plane is all broken up and there's just not really a whole lot of good strategies you can use there. You can always just kind of click points where you want, you know, like focus points. You do have some options here if you wanted that approach and retract to be a little bit bigger. So you see the approach and retract is this distance perpendicular to that surface that the probe is going to travel. If that's too close for whatever reason, you can go down to your properties here and uncheck inherit, and you could increase that distance. So I could make the approach and retract 5 millimeters instead of 2, and you can see now that's a greater distance for whatever reason. And these get inherited as some defaults, but yeah, that's kind of the idea there. You can also still add the approach or the clearance planes as you see fit. But now I could go ahead and just run this. It's going to move to that clearance plane first, then go down, now take that 2 millimeter travel hit, and then just drive over. Now, it's possible that I could place these points outside of the machine travel. That's something to consider. If it says you're going to hit a limit, it just means you've placed points that the probe physically can't get to. So reconsider your point placement. I could make that error happen pretty quickly here. Again, that's a big reason why when we're trying to, you know, discuss the right machine for your group, we might be suggesting a machine that's a little bit larger than what your part size would appear to require, and that's because touch probes, they're off axis, they're offset from the optical axis. So you do lose a little bit of travel in that respect. Okay. One other technique I wanted to show you real quick with this probe while I have it on here is the idea of a cutting plane. So for example, let's say I want a profile of a 2D curve right here on this set of radii. Now I can't, they're actually cylinders, so I can't just treat them as one surface. But what I could do is I could create what's called a cut plane. So I'm going to go into my metrology tree right here. This is this button right up here. This kind of keeps track of my alignments, any system, machine alignments, or anything like that. But I have this option here called cutting planes. I'm going to right click. This could be really useful for people probing when you want to probe at a certain height along a complex curve. So I'm going to say create, and what I'll see then is this cutting plane. Now it's oriented this way based on these I, J, and K vectors. And what that describes is the orientation of an arrow pointing straight out of this plane. Now if I want it pointing straight up, that arrow, or if I want this to be oriented with the XY plane, I'm going to make this 0, 0, and 1. Okay. Now notice my plane is kind of parallel with my XY plane. It's also offset at negative 60 millimeters because my Z0 is right here. So I'm going to make that negative, let's say 1 millimeter. Now do you see where this plane is? It's cutting across my part parallel with the XY plane at a millimeter down from Z0, which is this top surface. Now I can choose some geometries here. Let's say these 3 cylinders that are technically unique entities, and I can say cut. And what that does is it creates a whole new geometry that wasn't on the CAD model that I can now reference for the purpose of a contour type measurement. This can get pretty useful. We'll talk about this more as we deal with lasers and stuff as well. But now I'm going to measure a curve 2D, and this is really something that we couldn't do in MeasureMind because we couldn't calculate a complex curve. We could do each cylinder as one cylinder and hopefully blend them together, but in reality, you just weren't doing this right. And it was more about calculating the deviation that we couldn't do correctly. So I'm going to go ahead and select these curves. And if I look at them, oops, I got to select all 4 of them. Okay, now I've got these 4 curves right here are part of one feature, 2D curve. Okay, it's a progressive curve because each one of these radiuses is different from the last. But now, because I have that line in there, it gives my touch probe something to use when I want to do path generation here. So it knows where that is. I can say, give me, let's do 18 points. Okay, I'm going to get 18 hits. I'm going to start a millimeter from the end here and stop a millimeter from the end here. I'm going to say generate that path and hit OK. Now there's my path. The other thing I probably want to do is add that safe approach and retract. Always a good idea because I know it's not going to crash into my part on the way to that feature. Okay. Now as a safety precaution, I might set my program marker right there and just hit run. And now it's going to take that kind of complex curve for me at that exact 1 millimeter down from Z0, which is the top. So there's a lot of instances where this would be pretty useful. Just remember you have those cut planes in there. You can make as many as you want per program, and then they can be pretty helpful. If I wanted to measure this as a 3D surface rather than a 2D curve, I could copy this curve down in Z or up in Z every millimeter, depending upon how much real estate I have, and then have a bunch of these curves, and then I could basically construct them into a profile of the surface and get a good value there. And what's really nice about this too is, you know, if I look at the points that I just measured here in my top view, it gives me some indication about how this thing is behaving. Maybe not. I gotta do this in the profile. So if I do a profile of a line here now, I can see as I constrain this how those points are behaving, which is something, again, when we're talking about the value of graphics, what that does for us to kind of understand what's happening with these dimensions. So if I look at those individual points, based on the alignment I have, I can see that this whole thing is rotated kind of this way and this way. So the feature was just put in there a little wrong. Now I got a really tight tolerance on this, but you get the idea. That could then be reported out. I could change these graphics as well. This is kind of going off topic, but why not? So there's some cylinders. It's a little easier to see. And then that would be put right into my report down here as I rerun this thing. Yeah. Now, if I go and grab a different tool, so in this case, I'm going to grab the training star. It's going to ask me to unload this one. I hit OK. And then I'm going to load my training star. Now you'll see that actual star there. So what that gets me is, you know, I've got different tips here. I can't use tip 4 and 5 because we didn't calibrate them, but I can use tips 1, 2, and 3. Whichever the green tip is, right there, you can see that's tip 1. That's the current tip I'm using. If I'm trying to measure with this, but I have tip 1 highlighted, I might have some weird things happen. So just bear that in mind. Like, for example, if I wanted to measure this cylinder, what do I got? If I want to measure this cylinder on the right here with tip 2, I better go and make sure I'm using tip 2. And now tip 2 becomes the active sensor. So now I could kind of do the same thing I was doing before and use that touch probe. Make sure this vector looks a little bit better. It's pointing out. Wouldn't hurt anything either way. And now I can just say, what do I want to measure here? So this is where I might have to play with my values here. So you see how it's trying to measure top half of the cylinder? It doesn't know any better. So I'm going to say I want to go from 0 to 180 and just start playing with these. Now, do you see how it, or from 180 to 360? Okay, so now it's using that bottom edge. Maybe I go 200 to 360. And I can see what it's doing to these points right here. Oops. My keyboard setup is lackluster. And so there's 180 to 340. The other thing you can do is, rather than play with those numbers, you can just drag these things, little handles here, and it'll kind of tell you, here's what you're measuring, 194 or 200 to 193. Okay. I also got to consider how far into this part I can actually get. So my distance from start, maybe I want to make that like, I don't know, 15 millimeters. See how they all come out now? The start means the beginning of the arrow to the end. That's the end. Okay, so that's our vector arrow. And that's kind of defined by the actual cylinder or the geometry of the feature in question. So maybe that's a little aggressive. We'll go 12 millimeters. I think I should be able to get to that with this number 2 probe. I'm also going to, I can display the test path. So now I should be able to see, am I going to shank out right there on that cone, you know, at the shoulder of this thing? Let's go ahead and try it out. I'll say generate the path. And I'm also going to do a approach and retract from. Okay, so now it has to move out there in order to take that first hit. So let's go ahead and run this, but never hurts to keep one hand on your start stop button in case something's not happening the way it should. And that looks like it's doing what it's supposed to be doing. And now we're measuring with that. So this will kind of run us out of time here. I know there's a lot more we could explore. I just wanted to get you guys to the point where you can, you know, build and calibrate a probe, you know, configure an artifact, and then actually use it. How do you use it? Play around with it. I can't stress that enough. You have to use this stuff or you won't know it. You don't even know what questions you don't know right now. So in order for you to generate those questions, you need to use this stuff, and then we welcome the questions. That's how we get better. If our user base is having success with this, we're succeeding. If not, that's our fault. But we need you guys to reach out to us and let us know if it's working or not working. Plenty of resources around here.